Okay, guys, so we're dealing with waves, okay? And so we need to understand something about waves before we can understand how waves interact with matter. So as we look at waves, okay, we want to think about what waves do when they meet each other. One of the neat things about waves is when waves meet each other, they can pass through each other. So if I had a wave that was traveling in this direction, and it met a second wave that was traveling in the opposite direction. Okay, so they're coming out at each other, and they meet here at a location in space. When they meet, they can pass through each other. But where they meet, well, let me draw this in a different way for you. Let's say that I have a wave pulse. It looks like this and is traveling in this direction. And over here, I have another wave pulse. And they're traveling toward each other. Okay, when those wave pulses meet, so let's kind of look at them meeting here. Let's say when they first meet, okay, I can get a real funky looking thing like this where they start to overlap each other. And then down the road, okay, when they're both sitting on top of each other, I get a nice double fat. Let's see, that was that. So that, I'm going to have to draw way down low here. I get a really tall. And then once they've passed past each other, they move through and go on. So you could think of this as image 1. Here, that's image 2, 3, 4. Waves pass through each other. And where they meet, you get a combination disturbance. Okay? Now, where they meet at that common point, we call that interaction interference. And interference can be constructive or destructive. Now, constructive interference, they add together to give something bigger. Than the individual waves. What I was drawing before was constructive interference. I got something bigger. Destructive means that they add together to cancel each other out. Okay? So it destroys. Constructive adds, destructive destroys. Now, if we think about it, if the waves are in phase with each other, they're doing the same thing at the same time, then I get something that's a lot bigger. Constructive interference. If the waves are doing opposite at the same time, I get destructive and they cancel each other out. Okay? Constructive interference, destructive interference. Now, prettier pictures in my notes, but, I always have to draw. Now, waves also show something called a diffraction pattern, or an interference pattern. And occurs when waves encounter very tiny openings that are about the width of a wavelength. So if I have, let's say, a wall here, and I put two openings in the wall. And over here I have a screen. Okay? Now, if we were to have waves coming in at this wall, think about being in a helicopter flying, right next to the shore, and you can watch the crests of the waves coming in. Okay? When they meet these openings, something really interesting happens. When they come out the other side, we get, I'm not drawing them super evenly, so forgive me. They come out curved. Okay? Now, same thing happens here. If I look at this spot right here, and I think about the two waves meeting, at that spot right there, they're doing the same thing at the same time. This is constructive interference. If I'm at a spot right here, okay, this wave is going up, but this wave is going down. This would be destructive interference. Constructive, destructive. Okay? So we've got constructive and destructive interference going on. Now, I've got a pretty picture of what happens as the wave goes through the opening, okay, in your notes. So let me show you, okay. When the wave moves through the opening, it bends and gives us a curved wavefront on the other side. That's referred to as diffraction, okay. Waves do that, particles do not. If I were to fire BBs at those openings, they would pass straight through. Okay? Now, when we do two or more slits, we're going to get a light or dark pattern on the screen. Places where we have constructive interference and destructive interference. Now, pretty picture in your notes. Okay, you can see it right here. Now I'm going to try to show this to you with my drawing. So if I were to draw an up and down line here, grab a ruler. Let's use a ruler to make an up and down line. Okay, so if I make an up and down line here, at this spot right here on my screen, I get a nice bright spot. There I'd have a dead spot. Let's see. So if I came down here where crest meets crest again, I get a bright spot. So we'd have a pattern of bright spots, dark spots, bright spots, dark spots. That's what's called an interference pattern, because I can see where the wave is adding together constructively and destructively. Light shows interference patterns, particles do not. Okay? Something else that light does that particles do not is refract. Refraction is the bending of the pathway traveled when light, and I'm using light generically for all electromagnetic radiation, encounters a new material you could also call it a medium, angle to the surface. Okay, what does that mean? Let's say I had a blocks of plexiglass here. Okay, I have plexiglass. Now, one of the ways that in physics, okay, we represent light is we'll draw an arrow showing the pathway that light is traveling. Think of it kind of like a laser beam. If I were to shoot a laser straight on at this piece of plexiglass, it would go straight through. But if I shot it at an angle, okay, so it hit at an angle like this, what we'd see is it would bend. That would be the straight line pathway, but this is the pathway the light actually took. Okay? And then when I get to this point right here, it bends again. This is referred to as refraction. Light does this, particles don't. So if we had a pool of water here, let me draw a pool here near the center. Okay, so if I had a pool of water, water, okay? If I were to throw a rock